Okay, hi everybody, welcome back. We're going to start off, we're in lab 3 now, and this first video is going to be, we're going to run your first analysis of variance in R, and everyone remembers their first time, so this will be fun. I want to start off, first of all, you should have already read the first page of the lab handout, but I just want to stress a couple of things. If you see here, this here is the general representation of a linear model that we're going to be using. And this is what I've been talking about in lecture, where every observation, this yi, has a unique address and can be found by specifying the grand mean, mu, of the data set, plus the effects of whatever treatment groups that individual is in. Where we're dealing right now with just a simple CRD, so there's actually only one factor. And so this kappa 1, kappa 2, and so forth, we have just tau 1, that is the treatment effect, and then at the end we have the error term. When you move into R to specify the model, we're going to be using this LM function, the linear model function, and then this part here is a statement of the general linear model. And in this case, for a CRD, it's just the response variable is explained by, and that you can interpret that tilde as explained by, the treatment effects. And you'll notice that although the grand mean, mu, and epsilon error are technically in the linear model, you do not specify those in the linear model statement because R assumes every linear model has a grand mean and also has an error. So you're basically specifying all the other terms. With that in place, once you specify the linear model, that's going to create a linear model object. So here's an example. You're going to specify a linear model. You're going to write it out and specify the data set. And that is going to create a model object. And then if you want to extract an ANOVA table from that model object, you have to use a second function, this ANOVA function here. So let's see that in the context of the first example here. I'm going to go ahead and open up the script for example 1 and pull that up here. So here we are. This is lab 3 example 1, and we're going to be working with the same Clover data set that I was showing you in lecture. So let's go ahead and import that data set. I'm going to import from a text file, and we are in lab 3. And it's lab 3 example 1, the CSV file. So click on that. In the script, I call it clover.dat, so I'm going to change the name there. It does have a header bar. This all looks good, so I'm going to go ahead and import it. And this is the same data that you saw in lecture. We have 6 different strains of rhizobia, and 5 replications within each strain. And we see over here in our work area, our session pane, that clover.dat consists of 30 observations of 2 variables. If you go down to the script that I wrote for this, we'll just start working down the script. I'm gonna run this str function. So I'm gonna ask for the structure of clover.dat and send that to the console. And we see that clover.dat is a data frame, and it has 30 observations of 2 variables. Culture is one of those variables, and it is a factor with 6 levels. And R immediately knows it's a factor because we actually have names in the headers there instead of numbers. And then we have the nitrogen level. This is a measure of how well that particular strain of rhizobia helped the clover plant fix nitrogen, and we have numbers for that. So we have a factor, we have our independent variable, and then we have our dependent variable, the nitrogen level. So the structure looks fine. Now we're going to run the analysis of variance, and it's very, very easy. You'll see here we have linear model, LM, that's the function, and then we have to specify the linear model, and here it is. It's that in level, the response is explained by culture, is explained by the rhizobia group that it's in. And again, no need to specify the grand mean or error in the model. So it's a very, very simple model. The data set is of course clover.dat, it's the one we just imported. And when we do this, we're going to create this clover.mod model object. So I'm going to send this line to the console. We sent it, nothing shows up in the console, but now we have shown up over here this clover.mod in our session pane, we could actually ask for the structure now of clover.ma. Let's take a look at this thing, and you'll see what pops up. It's a huge object, and inside this object, we'll just scroll through here. Inside this object are all the coefficients, all the model fitting that has happened. It has stored basically everything inside of this model object. And what we would like to do is reach inside this model object, all these different attributes that it has. Here's the model itself. It has the data itself. What we'd like to do is reach inside that model object and just pull out the juicy bits, the stuff we need for the ANOVA table. And in order to do that, we use the ANOVA function. So it's just ANOVA, lowercase a. We'll see there's a variation of this later on with an uppercase a, but lowercase a, ANOVA. And you run the ANOVA function on the model object that was created back here. Okay, so when you run an ANOVA in R, it's really a two-step process. You have to create the model first, and then you extract the ANOVA table from the model object. So let's send this next command over, and what you see is what you would expect. It actually produces an analysis of variance table. The response is nitrogen, great. And here we have the two rows in our table. We have treatment and error. In other words, we have culture and residuals, where residuals is error. Degrees of freedom for treatment is 5 because we had 6 treatments. We have the sums of squares, mean squares. It finds the F value, and it calculates the probability. So you can see from this we have an extremely small p-value. It's much, much, much lower than our chosen type 1 error rate. So in this particular case, we would reject the null hypothesis. We would conclude that some significant component of variation exists in this particular data set due to the treatment effects. Something else you can see, we can get some more results. We can run the summary function on the same model object, and we'll get a little bit different data from that. When you run the summary function, we'll scroll up here. So here's where we ran the summary function. It restates the model that we're using. It gives you some stats on the residuals. So the median residual is getting pretty close to 0, and it gives you the minimum residual and the maximum residual. And then it gives you a coefficient. If you were actually to fit this model into a multiple linear regression, something like that, this is actually giving you the estimates of all the slopes and standard errors and whether or not they're significantly different from 0. We're not going to worry too much about all that. And then at the bottom here, it gives you what the residual standard error is. That is just the square root of the mean square error. It should be. Let's go up here. Yep, your mean square error is 11.789. I think if you took the square root of that, you would get something like 3.433. But the big one I want to point out is this multiple r squared. This is an indication of how well your model is explaining what you're seeing. This multiple r squared is essentially a percentage of explained variation. And where that comes from is up here in the ANOVA table. This variation, this sums of squares here, this is an amount of variation that your treatments explain. And if you were to add this 847 with the 282, this would be the total amount of variation you're seeing in the model. So where that 0.74 comes from, this 0.7496, is simply the percentage of explained variation over total variation. And so we see in this particular case, the actual strain of rhizobia seems to explain an awful lot of the variation that you're seeing in nitrogen fixation. Okay, so we'll stop here, and we're going to pick up in the next video with testing for homogeneity of variance.